nonetheless, this is what we're going to have AX. So we're going to scroll down here, or you can just hit the 4 button, however you want to do that. If I hit the 4 button, I have myself in right now. Don't hit enter yet. We not only wanted to calculate the linear regression, we want to put it somewhere. Just calculating isn't always the best. Remember we cleared out our y equals 2? I want to put this into y1. So what I can do is, this is another step here. Notice this button over here, if you follow the mouse, it's called vars. That's short for variables. If you hit the variables button, and I go over to the y variables, I have the 4 options of function and parameter and polar. We're going to be working with a function here, so choose function. And notice it pulls up the list of y1 through y whatever. These are the same ones that you find in y equals 2. So where do I want to put this? Might as well use y1. I could put it anywhere, but since y1 is empty and that's the first one, let's go ahead and choose y1. So this is, after you hit enter, this is what the command should look like. We still haven't run this thing yet. We're still setting up the command. The command is that you want to do the linear regression with this form, a times x plus b. That's like an m. The slope is a. And then you're going to stick all of it into y1. Okay, there, vars, which stands for variables. Go over to y vars. Choose function, and y1 is number 1. Okay? All right, go ahead and hit enter. Now my enter will have these R values you probably don't have. It's okay. You don't need these R values, these are for me. Okay, do you guys have R values? Anybody have R values show up? You do? You have a huge calculator, somebody knows what they're doing. Those are good to have, but you don't need them for this class. This tells you, this R value tells you how accurate of a fit this really is, or estimates the accuracy. This tells me it's about 92% accurate. That's pretty good. So I would trust this thing. All you guys need is A and B though. So if you're not seeing R, don't stress. We need A and B. Remember, A is the slope and B is the y-intercept. So right now, if I wanted the model of the line that went through the data, I could write y is equal to 62.17, that's rounding, times x, minus 1315.53. This green equation right here. Notice it's y equals mx plus b. You know what y equals mx plus b looks like on a graph, right? It's a straight line. Now, instead of typing that into y1 though, go take a look at your y equals 2 now. You'll see that the calculator was nice enough to put it in there for you. And with all the decimals.
Is this from all the numbers that we plotted?
This is exactly where it's from. So when I hit the graph button now, I should see the scatter plot, and I should also see this nice line go right through the middle, like that. If indeed this is the line of best fit, according to this calculator.
You press enter?
I hit graph.
You just hit graph after that.
Yes, hit graph. Did you get it?
Hit trace. Yes.
Don't hit trace, hit graph. Trace will work though. Yeah, trace puts it up to graph nicely, so, and allows you to trace. Anybody not get this picture? Okay, let me see what happened here. Okay. Everybody able to get this picture? Very close. R values you tell you the accuracy of the. It's not really that easy. The R values are how well does this thing really model this? Is this the R values go from 0 to 1, the probability that it actually works. Anything below 80 and I wouldn't accept it. That's saying it just isn't linear. Some things aren't linear. We'll get to that. We'll get to that. Okay, here on the paper it tells you the on-base percentages and the run score. Let's see, if I have an on-base percentage, let me pick a number we don't have there. We have just about everything, don't we? 32, there we go. Do you see a 32 anywhere? Oh yeah, there's a. Okay, how about just straight 32? We don't have a 32, so let's go over here and say, all right, this particular team has an on-base percentage of 32%, exactly. What would be the number of runs you would expect him to score based on this data, of course? Based on this model, if you will, if a team has 32% on-base percentage, according to this model, what would be the runs scored? How would you do that? Second, calculate is exactly right. Second, calculate the value when x equals what? 32. And it will tell you the run score will be 673.9, so we'll round that up to 674 runs. According to this model. See, I have when x equals to 32, it gives me the y. You see what the model allows me to do now? It allows me to basically run any average through there because I now have a linear function, not just a random set of points. I can put in any value for a percentage and get the approximate number of runs scored, again, based on this model. This is by no means, guarantee or anything, but in statistics, we look at what's happened over and over and over again to make determinations about what's going to happen in the future based on that, right? If it keeps happening this way over and over again, there's a pretty darn good chance it's going to happen that way again, right? Not guaranteed, but certainly would put my money on this if I had to. I would like to see a little more data though, to put money on. But nonetheless, 32 corresponds to that point, which according to this model will give 674 runs. Okay. The other thing that might perhaps be a question here is, let's say we had a team that had 780 runs. Okay? What would be their on-base average? Again, according to this model. If they found out that this team at the end of the season had 780 runs, and they wanted to know, based on this model, what their on-base average or percentage is, what would you do with the calculator? What we have to do this time is you go to y equals, you go down to y2, and put in the number 780. And then hit graph, and you'll see that line represents where 780 runs are scored. And we would want to find out where that intersects with our particular model, which is right here. How do you find the intersection of two lines on this calculator? Remember back to the first week of class, right? We talked about how to do the intersection. Second, to calculate the intersection, number 5. And all you have to do is get this thing somewhere close, and really with lines it can be pretty far off. And hit the enter button 3 times. 1, 2, 3. You're actually answering 3 questions. It's not some fancy enter 3 times button. You're answering first curve, second curve, and guess. But it's going to be the same every time if you have 2 lines. Yes, it'll be the first curve. Yes, it'll be the second curve. And yes, you're guessing at it because you just moved close to it. That's the whole point. Notice what it says here. For 780 runs, this model says you have a 33.7 on-base percentage. Second calculate, or second trace. Option number 5. Move somewhere close and hit enter 3 times. Now, if you look at the data, let's see how that corresponds with the data. Somewhere near 33.7, is there anyone? Here's 33.8, and 33.8 had 753 runs, and then 33.8 had 755, and they're saying this 33.07, excuse me, is going to be 780. So no, it's not perfect, but it's within the ballpark. No pun intended. Actually, I guess the pun wasn't. Okay, so you get the idea, right? Everybody said ballpark. Oh, baseball. So, all right. So you understand what we're doing here? I'm not really worried about getting these questions correct on much of this example as can you get these pictures right now. Everything we're going to be doing is based on the idea of putting a scatter plot up, getting some kind of regression, in this case linear regression. And why did I choose linear regression? Well, it's the first one to start with that makes the most sense. Not to mention, that just looks like a line, doesn't it? We're going to be working with different regressions though, so don't get used to just linear regression. The first thing you're going to have to do is get the data into the calculator and onto a scatter plot before you can even tell me what kind of regression it is, right? But just looking at a list of numbers is hard to determine whether it's going up or going down. You can make some of those determinations, but what if you had a scatter plot